Okay, I'm going to get back to this Luxman now, and I figured probably the smartest approach to take is to get the power supply going first. There's been a lot of components removed from here, so I'm going to have to replace those and see what we get. They don't have any of the voltages on the schematic, but I was able to figure out what most of them were supposed to be from the table they put next to the schematic and trace them back to each one of these points. This is our positive 30, negative 30 supply, 30.5. This is our positive 126, negative 126 supply. This is our negative 53.3, positive 53.3. And I wasn't sure what we were supposed to have here, but I believe this is negative 85. And this is negative 8.2 and positive 8.2. We'll see how close we come to the mark there, but I'm going to have to get a lot of work done before I even do this. And we'll take a look at the board before I get started, and I'll talk about what my approach is going to be. Okay, let me get that out of the way. You can see scorch marks on this board. I forgot to order a replacement bridge rectifier, but I got one I think is going to be a good match. And I put it in a heat sink. I'm not sure if I'm going to be able to get it in here or not, but I'd sure like to. So if I can, I'm going to install this. I have to see if the orientation is going to work out. But I wanted to get a heat sink in here because of the tremendous amount of heat. Now, I think this is a 2 amp rectifier. I'm putting a 4 amp in. That'll help. I got replacement fuses in here to put it back in here. Gonna replace all these capacitors because the heat in here is just ungodly. And I got to make note of why these resistors were lifted and solder those back in, replace all these capacitors here, and then we'll see what kind of voltage we have and take it from there. Okay, so I managed to, I had to give the bridge rectifier heatsink a bit of a haircut, and I replaced this capacitor, 6800 microfarad at 16 volts, and this is an 8.2 volt supply. I initially thought there was a positive and negative 8.2, but it doesn't reference ground anywhere. So here's what we just worked on, and we should get 8.2 volts. I didn't trim the leads off the bridge rectifier, so it would give me a handy place to check. So let's see what we get when we fire it up. And of course my lamp is giving me trouble. Okay, so here's our meter. We're tapped across the positive and negative on the bridge rectifier, and we fire it up, and we get about 9.1 volts. I said 8.2. I had it in green because green is for guess. The red ones should be about what they should be. So we got that supply up and running. Okay, so replacing the bridge rectifier due to heat concerns and putting a heat sink on it here and replacing this capacitor allowed us to get our power supply up and running for the positive 8.2 volts. Now we got something like 9 volts. These power supplies are probably all unloaded. I don't know where this goes, but if you just look at the heat that this experienced, they're pulling a lot of current out of here. So I'm gonna have to look at the schematic further, see what this feeds. This power supply is now good. This power supply here should already be good because these are the main filter capacitors, and they're showing negative 50 and positive 50. I did take a quick look at that, and they are okay. I'll check them on screen here and show you what I got. The next power supplies I'm going to do are going to be the negative and positive 30. There's a lot of fuses missing out of here, and I suspect this may be one of them, so we'll check that out. But anyhow, this supply is now good, and this supply is also good. So we'll check that, and then we're going to work on this. Okay, so our filter caps are just lined up right along there. So if we go to the back of the unit, we can see that they're here, laid out in a line like that. And the common points are between the two pairs, so we should have two sets of negative and positive voltage. So I'm going to pull the camera back a little bit so you can see the meter on the screen. And we're going to check those, turn it on. Comes out of protection. It should. There's nothing in it. There are no outputs, no driver board, no tube board. So these are going to be unloaded, and therefore instead of negative and positive 53, it's going to be a little higher. There's our negative 59 here. Positive 59 here. Negative 59 here. Positive 59 here. So the power supplies for the outputs are looking okay. So we have two more power supplies. We're going to turn this off, and I'm going to discharge those caps. Don't know if I've ever shown you this. I want to make a different discharge tool with light bulbs, but this is what I have. I took a clip lead, chopped it in half. I got a 3-watt 51 ohm resistor in here. These are good for discharging. You don't want to just put a screwdriver across them because it'll arc. This will discharge them slowly enough, but at 51 ohms, it's quick enough to where you can just charge these, because with nothing on them, they just discharge really slowly. So we got to discharge these. So I'm going to discharge those, and then we're going to take a look at the positive and negative 30 volt. Okay, so I had to replace fuses that were missing on here. There's a fuse here and another fuse here that feed the positive and negative 30.5 volt supply. These capacitors are missing too. The schematic says T160 milliamp. The board has stickers on it that say 1.6 amps. So I'm not sure what's going on here, but they look like factory stickers, and here's a picture of them. But anyway, I replaced these fuses here and here that feed this set of diodes, and we're going to replace these capacitors here and here. Now the board has had some substandard work done, and when I say that, there's a practice I totally despise, and that is cutting traces on the board for troubleshooting purposes, and that looks like what was done here. I don't know when it was done. When you have a unit as old as the stuff that we work on here, stuff that I work on here, it's not unusual for them to have been on the repair bench several times with work of varying degrees of quality. So no telling when that was done, but that is not a practice I've subscribed to. You can usually find another way to isolate the supply from whatever it's feeding without mutilating the board, and I can't think of any other way to put it. In any event, we're going to be putting our capacitors in here and here. There's our C1303, I'm sorry, 1203 and 1204. So let's get those put in. I got my visor on because the bigger it is, the less of a chance I'm going to make an error. And one thing I don't like is when you get into something like this where parts have been removed, you have to trust the silk screening on the board, which is good, let's say 98-99% of the time, but there's always that chance that they made an error. It's not unheard of. So I'm going to put my big head in the way here for a moment, and it looks like the polarity goes in like this. Now we're going to have to bend these leads, all right, because the old capacitors were physically much larger, and we don't want to put any stress on the leads. So we bend this lead out like that, 90 degrees, and then we put a bend in it like so. And the reason for this, if you've watched my videos, I've mentioned this, you don't want to put stress on the rubber seal at the base of the capacitor because you don't want to break the integrity of the seal. What happens to electrolytics over time is they dry out. Even with the best of seals, no seal is perfect. So, big head back in the way, and that goes in like this. There we go. And now that fits close to the board with no stress on the seal. Gonna have to do the other one the same way. And I just kind of guesstimated. I've gotten pretty good at that over the years. So now we have something that looks like this, and we won't have any stress on the rubber seal. All right. So, scratch what I said about bending the leads in this particular application, because what I had failed to notice was, if you look very closely down here, I'm going to put some light on here. But anyway, there are two holes on this side for capacitors with different lead spacing, so I did not have to bend the leads on this. Okay, so I unbent them, straightened them out, and pushed them through the board. And now we're going to solder them in. I'm going to leave the leads on here to give a convenient place to measure the voltages, and then I'll give them a haircut. Okay, excuse my big head, I just want to inspect the work. That looks okay. All right, so now I'm going to put the meter back in the frame here, and I'm going to move this back, and I'm going to turn that light off because I think all it's doing is giving us additional glare. All right, so I'm going to pull this out, go back to using one of these. Okay, so we are probably looking at something like this. This should be our negative, or that should be the negative. Negative 31, relay's not happy. And positive 31. I'm going to turn that off. I don't know what's going on with that relay. We're going to have to look at the schematic. But anyway, that gets two more of our supplies up and running. Okay, so that protection relay was buzzing. And this unit has a protection integrated circuit. And this is the relay driver transistor. And it is powered directly from one side of the main power supply. If you recall, our main power supply, the big filter caps are here and here. Interestingly, they have a common bridge rectifier between them, but they have separate left and right. And let me look. No, I am mistaken. Even though the board says left and right, it looks like they are common. So we have basically one big power supply here, positive and negative 50, and that is what powers this guy here. Now you can see the positive side goes up to here, and the negative goes to here. And I know that because I looked at the data sheet for this IC. This is the block diagram, very similar to what you saw there. Now it says substrate here for 5, but if we look down here, let me just tilt the camera, make sure it's in frame. We have negative VEE, negative 50, up to negative 50 coming in here through an 18K ohm resistor. And we have our positive VCC here through another 18K going into pin 9. So that's how I determined what our power supplies were. And that's what's powering this chip. I think the power supplies are okay. We're going to have to look in here. This unit's had a pretty hard life. And also, as we're going through the power supply, I don't have it here because I zoomed in on these parts. But we also have over here 2 3-terminal regulators and a bridge rectifier here and a fuse. So we're going to take a look at this also as we do the power supply, because I want to show you something on this board right now. I'm going to move the camera so you get a good look at this. And I'm going to move the unit toward me. The transformer should keep it on here. But if you look down in here, we have two regulators, here and here. Let me get in a little closer because it's important that you see what's going on here. This is very, very similar to the surround sound receiver I just looked at, because if you look here, this one seems to be okay. This one's unsoldered itself. See how floppy that is? You can always tell when something like this, you're going to have broken solder joints. So I'm going to pause the camera and move it. We're going to look at the bottom and see what that looks like. Now I want you to take a good look and watch here. And I'm going to jiggle that on the other side of the board. These are classic broken or bad solder joints. You see that? We need to resolder that. And also, since those are TO220, I bought some heat sinks and we're going to put those on. I'll show you what those look like. Okay, so I bought these on Mouser. These are slide-on heat sinks for TO220s. And they look like this, all right? And they just slide right on like this. See, even the hole lines up in there if you have hardware, but they'll stay on here. They probably work better with TO220s that aren't encapsulated like this, but this is what we're going to be using. We got to get the heat to draw away from this. And I know also there's capacitors near some of these hot points that are almost assuredly going to be bad. So we're going to be pulling and replacing those as we go through here. But these are what we're going to come across just going through the power supply. It's important to get your power supply up and running because that is the heart of any system. Okay, so I resoldered one of these regulators. Didn't bother to see which one it was. The soldering on the other one was okay. We're going to slide some heat sinks onto it. But sure enough, I checked both these capacitors. We're going to check them on the LCR meter. But whenever you have points of excessive heat, you really need to think about replacing or at least checking the electrolytic capacitors near there, because heat is the enemy. Heat dries them out, If they get dried out, they become ineffective, don't work at all. And sure enough, these read pretty bad. I'm going to take a look at the meter now and I'll show you how they were reading. Okay, so the LCR meter's back here. Let's get a better look at that. All right. That should be visible. So we had 1,000 microfarad at 16 volts. We look at that. We have, come on, about half of that. We got 450, less than half. So instead of 1,000, we had 450. It's a physically larger capacitor than this 470 at 16. And the smaller they are, the worse they usually look. And indeed, let's take a look at this 470 microfarad and see that it reads 1.2 microfarads and 96 ohms of ESR. So that's a bad cap. They both needed to be replaced. So I got those replaced. We're going to slide some heat sinks on there, and then we're going to see what our 12 volt looks like coming out of those. All right, this is one of those good news, bad news kind of deals. So I replaced both of those capacitors here and here, and also the missing one, which was a 3300 at 25 volt that went to the input of the regulators. And we can just take a quick look at that right here. These are our two 3-terminal regulators. We had a pre-filter cap here, 3300 to 25, and we also had our 1000 here, which was reading half its value, and our 470, which was reading almost 2 microfarads instead of 470. So we replaced these. We replaced the missing one here. I resoldered one or the other of these. I think it was this one. And good news is that our voltages look good, and it seems to have stabilized the protection relay. I don't know why. I'm not sure how that feeds in, because these go that way and I'm not sure where they go. But when I turned it on, there was a good solid click. The bad news is these slide-on heat sinks are not going to fit. I need to see if I can find a different type, because the wings here make them too wide to fit in a given space. And I know there are some other ones that just go straight up, which would probably be a lot better deal. I bought these for the driver board, and they'll be fine there. There's plenty of room for them. And I like having stuff like this on hand, so I bought 10 of them. I always buy in bulk. I buy 10 or even 100 of something, depending on price and how much I think I'm going to need it, or how close it is to going out of production, because we are reaching the point where through-hole components themselves are getting close to end of life. But anyhow, enough about that. Let's turn this on. Good solid click for the protection, no delay, but we'll look into that when the time comes. And we have 12.2 volts out of one of the regulators and 11.88 out of the other. So that looks good, and that brings up another point. I'm not sure how this feeds into the protection circuit, but you notice it's not buzzing anymore. And that point I want to bring up is, if you find a problem, fix it. When you're troubleshooting something, you come across a problem, you go, well, that can't possibly be my issue. Well, you know, it might be. I will freely admit that when it comes to circuit analysis, I am not the best. So if you find a problem, fix it, and you may be surprised, more often than not, it'll fix the problem you're having. Whether you think it affects it or not, it may. So anyhow, we're going to go back, and I believe we have one last power supply, which is 120 volt positive negative. Anyhow, we'll look at the schematic, and then we're going to tackle that. And I think that'll take care of the power supplies for this. But I'm going to take a good look at the schematic, because I did miss these 3-terminal regulators. Okay, so these last capacitors that have to go in here to replace missing ones are 220 microfarad, 160 volt. So let me just get our diagram back up here. So this is going to be where we're working at now. We're going to be working right in here, and that should be 126 positive and negative when we get done. So I need to make sure we have a fuse, replace these missing capacitors, and we'll check the voltage and see what we get. Okay, so I've got the fuses replaced, got the capacitors in. We have one here. I believe this is going to be the negative side, then these two leads here tie together and are most likely ground. That should be the positive side. So let's turn it on and see if we get any smoke or flames. Nope, but on the other hand, we're not getting squat out of here, so I need to check to see if the diodes are in, or if I've done something or overlooked something else. I replaced the fuses. Now these say T 160 milliamp, but the board says 1.25 amps. So let me take a look and see what's going on here. Okay, this is where attention to detail really pays off. This unit is currently off. I had neglected to put the ground of my meter up here. That's why we weren't reading anything. So when we turn it on, we're going to get over 120 volts. We get 137 volts there, and we should get the same thing negative here. Yeah. Now remember, all these supplies are unloaded. I'm not concerned that the readings are high. The 12 volt regulators look good because they were regulated supplies. None of the rest of these are. So this gets all the power supplies up and running. I took a second look at the schematic and I didn't see any others. So this is phase one. All our power supplies are up and running, and interestingly enough, I didn't look at what the regulated supplies feed, but you notice now every time we turn it on, we get good solid protection relay. Clicks off, and you see, since these supplies are unloaded, they don't discharge very quickly at all, do they? So I'm gonna have to discharge those before I clip the leads, or I will get a nasty surprise. Okay, so we turn it on. Good solid click every time now. So again, find a problem, fix it. Okay folks, that concludes this phase of the repair of this unit. This is going to be a project. I kind of knew getting into it. I just didn't know how bad. I got the one set of boards back on this, and I'm going to have to show you this because this is another one of those attention to detail things that just turned around to bite me. Okay, so this is the front panel where the tubes lay in right here. And I was so fixated on making sure I got the spacing right. I measured it 2 or 3 times. I looked really closely as I was doing the board layout, and I was very happy when I got this, and I said, look at that. The centers are perfect. And let me get it into the screen here so you can see what I'm talking about. So those tubes would nestle in here perfectly. I never even noticed that the sockets are wrong. These are what they call sub-miniature tube sockets. I don't see a lot of tubes like this. Mostly what I see are what they call no-val basing, N-O-V-A-L. Tube sockets have names, usually not alphanumeric nomenclature. So once I got the right tube sockets, I'm having the second set of boards made. Now this board, I think the layout was good. And I was a little concerned about how thin the traces were, but the voltages are not that high, and there's very little current going through here, so I think this is going to be okay. But I have since learned how to go in and make thicker traces on the boards, because while a board like this would be okay for voltage applications, you couldn't pull any appreciable current out of it because the traces are too skinny for that. You know, you need to have a certain amount of copper. So anyhow, that concludes this portion of the video. I do want to mention one other thing while I'm here. Those resistors that I thought were lifted are actually soldered in at an angle to get part of the body off the board. Now I'm going to take them out and I'm going to put new resistors in. I'm going to kink the leads. I bought this little dingus that puts kinks in leads. Thing confounds me. I always do it wrong the first time, virtually every time. I got to mark one side of this so I know which way to hit it, because I tend to do things like this, and this is not what you're trying to do. Anyhow, that's it. That's it for this video. I'm not sure where we're going to go next with this, but I may see if I can start pushing some signal up to where the driver board starts. And then we're going to have to tackle the driver board. There's a lot of components missing off of that, and we want to see if we can get some signal through that next. That is actually why I bought those heat sinks, and they will be fine there. So enough rambling. This concludes this video, and as always, I thank everyone for watching, and I like giving back to the community that has really given me so much. Thanks a lot, folks.